Now we're going to look at some problems of mean value theorem. Actually, there's only one problem that has to do with mean value theorem, whereas the other one are just miscellaneous problems that has to do with continuous functions. Now let's look at problem number 1, where it says f of x is the absolute value of x times log of x, again, absolute value, and f of 0 is some kind of positive value, we'll call it, that we'll assign it as e. Now, given that, we want to show that f is not continuous at 0. Now that can be shown if you try to look at the limit, of course, but in this particular problem, we don't want to, we are specifically instructed not to look at the limit, but rather use the mean value theorem. So here's what we're going to say. First, that because the log function, now remember how the log function works. The log function is such that between 0 and 1, the log function is negative. So f of x is less than 0. So f of x is less than 0 from 0 to, let's see, from 0 to 1. Okay, it's not defined at 0, so we'll just go from 0 to 1, not including ends. And then f of 0 is equal to e, which is bigger than 0. And that means that then therefore the function is not continuous, because by the mean value theorem, if in this particular interval, if it's continuous, it has to include, f has to include every single value that goes from 0 to e. But f is already negative in the entire range. So by the mean value theorem, that is not possible. Therefore, f cannot be continuous 0. That's it. So the conclusion is f not continuous by mean value theorem, which is called the MVT. Anyway, so let's go move on to number 2. Now, number 2 says you have a function that's f of x is the square root of 4 plus x squared. You have to show this particular quality of f of x. That is, the increase rate or the variation rate of f of x is less than the variation rate of x itself. Now, and the purpose of showing that, once you have shown that, then you can show that f is therefore continuous, because then the limit as x approaches to x0, the limit of f of x has also to approach f of x0. Now, to show this thing, I'm gonna, well, because it's a square root, the algebraic manipulation will tend to be more difficult. So we're gonna do this the easy way. That is, we're gonna use an algebraic proof. Now, the square root of 4 plus x squared just means this, the hypotenuse. If you have a triangle, okay, one side is 4, the next side is x, and then the hypotenuse is this square root we're talking about. So we'll draw it down like this, and this is f. We'll call it, since we have two x's, we'll call it, the first one is just x, and then if you have a different x0, so this whole thing is x0, a different one that we'll assume is longer, doesn't matter if it's longer or shorter, then you draw another f, that's the different value of f. And since this is called x0, we'll call the value f of 0, okay? And so you have these two lengths, and what you're trying to show is the difference between these two lengths is actually smaller than the difference of these two lengths, which is this distance right here. All right, we'll call it h. This distance is h. We'll call it h1, which is x minus x0, as demonstrated in the graph. Now, f is this distance right here. Okay. Now we will drop a perpendicular line all the way across. This is perpendicular, and as a result, now notice that f is then the hypotenuse, this length is the hypotenuse of this particular right angle triangle. Therefore, if you measure f all the way here, f is going to extend. So this distance right here is going to be f on f0. So this thing right here, okay, it goes beyond the perpendicular drop point. So that's all. This distance is f. Okay. So this thing right here is what we're looking for. That is f of x minus f of x0. Now this distance right here is less than one side of this right angle triangle, and therefore it has to be less than h, because because one of the sides, in any right angle triangle, the sides that touches the right angle is going to be less than the hypotenuse, and that actually concludes our proof. So this is f minus f0 in absolute value, and therefore it's less. It's that simple. So let's move on to problem number 3. Problem number 3 is slightly more convoluted. It says if you have a function f and you don't know what it is, you're given that is defined well everywhere. It is continuous at x0 equal to 0, and it has this particular curious property. Okay, fx plus y is fx times xy, and this property satisfies for all xy. What you're trying to show then, or you're required to show, that f is continuous at all x points. So to prove this problem, first you will figure out something. Now, if they give you such an odd situation, then you think about it, then that means f of say f of y, okay, if you pick any point y, is equal to f of 0 plus y, because y is just a real number. And yeah, let's play with 0, see where it leads us, right? Which is equal to f times 0 times f times y, according to this formula here, which means now, so fy is equal to f0 times fy. My y looks almost like a g there. That's a little better, which means f of 0 equals to 1. So that's what you can get out of that formula. But that's not the only thing you can get out of it. So that's step 1. So you know f of 0 is 1, but you don't know what everything else is. That, if you look at it long enough, you realize that reminds you of functions such as, what kind of function where addition is the same as multiplication? Well, the exponential functions, that would be one thing. But we don't care if it's the exponential function. We're just trying to show that it's continuous. So let's move on. So let's consider this. Then you consider the value f of x plus delta, where delta is a small number, okay, minus f of x. What does that get you? And in absolute value if you want, because we're talking about continuity, and the definition usually includes absolute values. Then this thing, again by this interesting formula, is f x, let's see, times f of delta, okay, minus f of x, which is, then you factor it out, which is equal to f of x times f delta, okay, f of delta minus 1. All right. Now, so then you have this value. Now you notice that as delta goes to 0, f delta goes to 1, because f0 equals to 1. Okay, this whole thing will go to 0. So that as delta goes to 0, this expression, this goes to 0. And that would mean that, therefore, this is just another way of saying that f is the limit of, therefore, this just means that the difference as f goes to, therefore, this is just another way of saying x approaches x0, f of x equals to f of x0. That is, the function is continuous.